Told you guys that the old one was up. Okay, today we're going to talk about binary relations some more. We're going to work on composition and closure properties. But first, let me give you a little bit of help on, what, homework 7? Is that what's due today?
I could have swore it said the 25th on there. If I misread it.
No, it does. It's just for the sections of basic.
Okay, so we're going to talk a little bit about homework 7. There was one problem where, can someone remind me of the recursion problem where you had to find closed form? S of 2 to the k?
S of 2 to the k is equal to 2s 2 to the k minus 1. You want to just borrow this?
No, plus 2 to the k?
Plus 2 to the k. There you go.
Okay, so the first part of this was to make a table, right? So we make a table for k and s of 2 to the k. So if k is equal to 0, then s of 2 to the k is, we had a basis, right? So we actually have to use the basis there. You notice the first thing when you try to make a table that you can't fill it out unless you have the basis. So don't ever forget when you're doing a recursion to put the basis, because no one will be able to do anything with it without it. Okay, so the next one, then it's going to be twice the previous one and plus 2 to the 1. So it's going to be 2 plus 2, which is 4. It's going to be twice that, which is 8, plus 4, which is 12. And that's going to be 24 plus 8, which is 20, and so on. So I told you a hint, and that was
32.
32, not 20.
32.
okay. Sorry, I was thinking of the difference instead of the actual number. Okay, so I told you a hint, and that was to think of powers of 2. And it's kind of hard to look at this table and see powers of 2 unless you write the powers of 2 next to it. So I write those next to them. They don't really look like the values that are up there, so I could do what with them? What did you do for this problem?
Try to figure out the differences between the power of 2 and the s.
So what's the difference between these? So what did you do to s of 2 to the k to get the difference? Divide, right? Divide by the powers of 2. So these are powers of 2. So if I divide those, I get 1, and then I get 2, and I get 3, and I get 4, and so on. Right? So that's how you find your pattern, because now we've just reduced it down to it being k plus 1. Right? So each of these is 2 to the k times k plus 1. So that's how we find the closed form. So then we get s of 2 to the k equals 2 to the k times k plus 1. That's how the table really helps. And that's why I said try to guess at the closed form, because there's not really another good way to do this. You just make a table and you start looking at powers of 2. Now the tricky part in this, after you got the closed form, that was the first tricky part. The second tricky part was actually making sure you did the induction correctly. So when you do the induction for this problem, just like we've done before, you assume that this recursion is correct, and you're going to prove that the closed form is correct. So our closed form was s of 2 to the k is equal to 2 to the k times k plus 1. And so your basis is what? K equals 0. So s of what is what I'm doing in my basis? S of 2 to the k, which is 2 to the 0. So I need to show that that's 2 to the 0 times 0 plus 1. That's equal to 1. And that's what my basis was. So what's your assume statement look like?
What you're trying to prove.
What I normally do is, what? Figure out, state the closed form for the thing on the right-hand side of the recursive rule, right? So I would have written, it doesn't matter if you put s of 2 to the k minus 1 or s of 2 to the k. But the important thing in here is that the thing inside these parentheses needs to be a power of 2, not just k. So when I was looking at some papers, I was seeing some k's in there, but we're proving this for powers of 2, not for any other numbers. So you have to be careful about what you write. So that's going to be 2 to the k minus 1 times k plus 1 minus 1, which is k. And then I prove for the left-hand side, s of 2 to the k is 2 to the k times k plus 1. And then how do I normally start a recursive proof? Like this? I write the recursive definition. S of 2 to the k is 2 times s of 2 to the k minus 1 plus 2 to the k, and then I do what? Substitution for s of 2 to the k minus 1 from the assume statement. So this is just like we've done all the other proofs for proving closed form for recursion. So that's going to be 2 times what? Substitution from the assume statement?
2 to the k minus 1 times k.
2 to the k minus 1 times k. And then I just copy over plus 2 to the k. And so I finished doing the algebra for that. That's equal to 2 to the k times k plus 2 to the k, which is equal to 2 to the k, if I factor that out, times k plus 1. Okay, so the important thing is to just plug along like you know how to do. And don't get stuck just because something looks a little different than what you've done before. You're still going to keep doing what you've learned how to do. And you've all done really good at induction, so just keep doing it the way you've been doing it. Okay, any other questions from homework 7? No? Okay, let's go back and talk about binary relations again. And you need to print out the packet from the website. It's got lots of examples on there, and you need to look at them. All of that stuff will be important in doing your homework and working the test problem. So please, please, please print that out and bring it to class from now on and look at it, all that good stuff.
When's our next test?
That is in the syllabus. I believe it's April 10th, but don't quote me on that. Okay, so beginning of every month, we've got a test. Okay, so binary relations. What is a binary relation? Who remembers? It's a relationship between two things because it's binary and relation, and it's a subset of a
Cross product.
cross product. Good. Subset of a cross product. That's one of the most important things. So it shows a relationship between the items in the two sets. So there's a point in the relation if there's the relationship stated by the relation, and if there's not a relationship, you don't put the point in the set. Okay, so let's do an example of a binary relation. I told you last time, we said, what is this useful for? And Brian's still not here to get what it's useful for, so I hope he watches this on tape. We're going to do an example with airplanes. So flights, we're going to do a relation between flights because we're going to need to do composition today. And composition is probably the hardest part of relations because it's sort of doing a lot of stuff all at once. So let's do an example. Between cities. We'll just say American Airlines, because that's the first one that pops into my head, not for any other reason. Okay, so we're just going to assume that the cross product is just going to be between the cities in the U.S. We're just going to actually look at a few cities. We're going to look at Raleigh and New York City and Paris, because I like to put that on my list. And let's also do San Francisco, SFO. Okay, let's say that there's a flight between RDU and New York City, and there's one from New York City to Paris, and there's a flight from New York City to San Francisco. And there's flights from New York City to Raleigh. And what else do you guys want? Anything else? Let's just make it like that. Okay, so here's an example of a binary relation. And since it's on the same set, this is my set that I'm doing the cross product. This is S, and R is on the cross product of S cross S. Is it symmetric?
No.
Now we have to get back from Paris and San Francisco, so we need to put some on in there. I meant to make it symmetric. Let me ask you this question. Do you want your flights to be symmetric? Sure. Yes, because we want the round trip discount, right? And we also want to get back home from where we came from. So,
but not if you're moving there.
But not if you're moving there. That's right. So, but we'd like these usually to have available flights to get back from where we go to. So we want this to be symmetric, so I had to make it symmetric. So you notice that I just had to add some things to make it symmetric, right?
Yep.
If I wanted something to be anti-symmetric, do you think I could add things to make it anti-symmetric? Okay, some people are shaking their heads. Why not? If I want something to be anti-symmetric and it's not, what's the problem with it? If something's not anti-symmetric, that means there's two symmetric points in there, right?
Yeah.
And adding something's not going to get rid of one of those symmetric points. That's why we can't make something anti-symmetric even if we want to. But we can take any relation and make it symmetric if we'd like by adding things. Okay? So you could also make something reflexive if you wanted to by adding what?
2 points that are like the flight from New York to New York.
Right, a New York flight, RDU, RDU, San Francisco, and Paris, Paris. That would make this reflexive, right? And do you think you can't make something asymmetric if you can't make it anti-symmetric, right? Can you make something irreflexive? No, you can't, because you can't take out things. If we're not allowed to take anything out, we can't make it irreflexive. So we can't make it irreflexive by adding things. How about transitive? Yeah, we could, because if we have AB and we have BC, then we can just add AC and that makes it transitive. So if we do that for all pairs and then do that sort of recursively just to make sure we've done it, then we can do that. So we can actually add things to make things reflexive, symmetric, or transitive. And we're going to talk about that right now since I started talking about it. That's called making the closure of a relation. So if you want a particular property for a binary relation, like reflexive or symmetric or transitive, you can just add a few things and make it that way. So what the closure is if I have a relationship R, the closure RC is the minimal set with two properties, so that the first thing, R is a subset of RC. So that means that you can only add things to R to make RC if I want to make a closure. And two, RC has the property you're looking for. So what we're doing is we're making the closure with respect to a certain property. So RC with respect to, that's what WRT stands for, is with respect to a property. And so the only properties that we can do this for are symmetric, reflexive, and transitive. And we just talked about why we can't do it for the other ones. Because then we can't have this relationship. And that's why we can't do it for antisymmetric or asymmetric or irreflexive. So we already talked about what kinds of things we'd have to add to make something symmetric or transitive, but let's make it a little bit more formal by writing it down, what we'd have to add. Okay? So if I have to prove that something is the closure, I'd actually have to prove. So if I'm given a relation R, and I want to prove that some other relation is the closure of that, I have to prove that R is a subset of that given closure. And then I also have to prove I have to prove it's minimal. That's the tricky part. And I have to prove that it has the property that I want. This is usually easy because usually you create RC so it has the property that you want. This is usually easy because you only add points, right? And minimal is the hardest one to prove. How do you think you might prove minimal? So if I want to prove something's the smallest possible thing, what would you do?
Common factors.
Somebody said common factors, so they're thinking about our proof that something was irrational, right? Which was a proof by contradiction. So we would do a proof by contradiction. You say, okay, assume it's not the smallest one. Then I could take some stuff out, right? If it's not the smallest, I could take things out and have it still have these other properties. That's what we'll do, is prove it by contradiction. So let's do an example. So let's say that S is 1, 2, 3. And R is 1, 2, 1, 3, and 2, 3. Okay, so what's the reflexive closure? So let's put RRC for the reflexive closure of that. So the first thing I have to have is that R is a subset of the closure. So I need to put all the points that are already in R. So what are those?
1, 2, 1, 3.
1, 3.
1, 2, and 1, 3, and 2, 3. So if I want it to be reflexive, what do I also need in there?
1, 1.
1, 1, 2, 2, 1, 3, 3.
1, 1, 2, 2, and 3, 3. That's why it's important to know what S is, because you have to have all of the reflexive points from S. So if S had more numbers in it, you'd have to put more points in, right? So we can actually write that the reflexive closure is going to be R union with some other set. And it's going to be points that look like XX as long as X is in S, right? That's the kind of points I have to add to make it reflexive. And this whole set represents all of them in that set notation. Okay, we're going to do some matrix representation of this later. But we can prove that this is the closure. Okay, so let's prove that RRC is the reflexive closure of R, if this is our definition right here. So the first thing is we have to prove that R is a subset of RRC. But RRC is equal to R union, U. Let's call this thing E right here. I have a reason for calling it E, because this is like called the elementary set or the identity set. So usually when it's a set, you denote it with E. If it's a matrix, you denote it with I. And we'll talk about the identity matrix in a little bit. Okay, so it's going to be R union E. And by definition of union, then R is a subset of this, right?
Yes.
So this is true by the definition of union. So now the next thing I need to prove is that RRC is reflexive, right? But the definition of reflexive says for all x in S, I have the point XX, right? So the definition of reflexive really says that E is a subset of my relation, right? So the definition of reflexive is the same as saying that E is a subset of that set. And so, again, by the definition of union, then E is in there, so it must be reflexive. So that's true, the same reason, definition of union. So now we have to do the hard part now, right? We have to prove that it's a minimal set like that. So if you don't understand what I'm doing, like the structure of what I'm doing, I gave you the definition of closure. We have to prove all the aspects of the definition. You're going to have to do some of these on your homework. So if you don't understand any part that I'm doing, you need to stop me. But there's always going to be 3 steps. First one, R is a subset of the thing you want to be the closure. The second thing is you have to prove that it has the property. And the third thing is you have to prove it's minimal. So you always have to do those 3 things if you want to prove a closure. Okay, so let's prove that this is minimal. So we want to prove RRC is minimal. So we do this by contradiction. So first we suppose not. Oops, sorry. This like square that I'm writing on, it's different. It's in a different place every time. So I think it's in one spot and it's not. So I suppose not. If it's not minimal, that means I can take a point out and it will still be the closure. Right?
Yep.
So therefore, if it's not minimal, then there exists a point xy so that if I take RRC minus the point xy, I actually have to put it in set notation because that minus is a set operator, right? So if I take out the point xy, still is reflexive, and R is still a subset of RRC minus xy. So let's call this R star right here, so we don't have to write that minus again and again. Okay, well, what happens if I take out a point? RRC is equal to what? It's equal to R union E. So if I take out a point, it has to come from where? Either R or E. So let's do 2 cases. Case 1, xy is a member of R. The other case is going to be that it came from E, right? So if it was in R and I take it out, then what? Then xy is not in R star anymore, right?
Yep.
Okay.
If xy is in R, but it's not in R star, then R can't be a subset of R star, right? So R is not a subset of R star. Since xy is in R, but not in R star. So R can't be a subset because there's a point that's in R that is not in RC. Sorry, R star. So the same sort of thing's going to happen if I take it out of E, right? If I take it out of E, then it's not going to be what anymore?
Subset.
So then what? E is not a subset of R star, right? If I take out x, y, and E. Right? Because E has a point xy that I just took out. Why is that bad?
Because
Well, I needed these 2 things. I had to have this and this. If I take it out of E, then it's not reflexive anymore. Right?
Aren't you taking out X and X?
It is an XX, but I'm just saying in general, if I have a point XY, when I first start this, I don't know that it's a XX. I just know that it's XY. And Y can be equal to X. It's not excluded just by saying that it's XY. So both ways I can take out a point result in me messing up my closure. So therefore, I can't take out any points, right? So therefore, I can't remove any points, which implies that RRC must be minimal because we have a contradiction, right?
Could you have stopped after case 1?
No, I couldn't stop after case 1 because I could have taken stuff out of E, possibly. I have to prove both cases. So if I take any point out of RRC, I have to see if that messes it up. Because if I can take some out, I'll take it out, and that'll make it smaller, and that'll be good. But I have to prove that no matter what I take out, I mess it up. Because you shouldn't be allowed to take any of them out because it's minimal. So this kind of proof, when you see it, you're like, oh yeah, okay, it makes sense. But if you were given this on a homework and you hadn't seen one, you'd be like, what am I supposed to do? Okay, so now you've seen one, now you know what you're supposed to do.
Could you explain one more time why case 1 failed?
Why did case 1 fail? Well, I needed to have these two things be true, right? I needed that R star was reflexive, and I also needed that R was a subset of R star. In case 1, XY, the point that I took out, so this says I can take an XY out so that this is still reflexive and R is still a subset. If I take XY out of RC, then R is not a subset of R star anymore because XY is in R, but it's not in R star. And I wrote that right here, since XY is in R, but not in R star. So I can't take that point out. You're going to do the same thing with symmetric. So if we want to prove the symmetric closure, we would do exactly the same thing. Symmetric closure is going to be another union. And it's going to be exactly this kind of proof. So let's figure out what the symmetric closure will be. And one of your problems for homework is actually to prove reflexive closure. Actually, this is one of your homework problems too. Aren't you glad you wrote it down? Okay, so let's figure out what the symmetric closure would be. What do I have to do to a relation R to make it symmetric? So let's go back to our original thing that I had. I had, what did I have? 1, 2, 1, 3, and 2, 3, right? That's the 3 points I had. So if I want to make this symmetric, what do I need to add to it? So if I want to do R symmetric closure, that's going to have R in it, so I need 1, 2, and 1, 3, and 2, 3, and then what?
2, 1, 3, 1.
I basically need to reverse all of these, right? So it's easy to look at something and see what to do with it to make symmetric closure. But the hard part is, in general, how do I write down what I do in general? So does anybody know how to take a set of ordered pairs and reverse all the ordered pairs?
For every xy, there has to exist a point yx. Is that what you mean?
Yeah, does anybody know how to, any set notation that would reverse all the orders for me? No, nobody knows it. It's called the inverse. Our inverse is to take all of the points in R and reverse them. So our inverse in this case is going to be 2, 1, 3, 1, 3, 2. So an inverse is reverse the orders of all ordered pairs. So that's like the inverse relationship. So if I say that A relates to B, the inverse of that is that B relates to A. So that should sound like it makes sense to you. Does it sound like it makes sense? Because if I want to go backwards, so say, remember that we drew arrows. If we had AB, we'd draw an arrow from A to B. If I want to do the inverse, I should be able to get back from where I went to. So I should draw an arrow from B to A. So if we draw the diagram, the picture of our inverse is going to be the same as R, except all the arrows will be going the other direction. Okay, so you can write that down. Picture, same as R, but all arrows are reversed. So it should make sense that if you wanted all the round-trip flights when you had your relation with the cities, that once you wrote down the flights out, you would want to add the inverse in to get back home, right? All the things that would reverse all the flights that you needed. That makes sense. So how do I write the symmetric closure in terms of R and R inverse?
R plus.
It's the union, right? These are sets. I have to take the union of them to put them together. So the symmetric closure is R union. Sorry, I keep drawing a U instead of just a regular union symbol. R union, R inverse. So that's the definition, or that's the set that we believe is going to be the symmetric closure. So let's go through, just without writing it down, let's go through what we would need to do to prove that this is the closure. First, we have to prove R is a subset. Exactly the same as the one we just did, right? Because this is a union. It has R in the union, so I don't have to do any extra work to make R in there. I have to prove it's symmetric. How do you prove something symmetric?
If the inverse is in there.
I have to prove that for every xy in the set, then yx is in the set. So you're going to actually have to do two cases. I'm going to say xy in here. If xy is in the symmetric closure, it either came from here or here. If it came from R, then yx is where?
R inverse.
It's in R inverse, so therefore it's in the symmetric closure, right? If it came from R inverse, if xy came from R inverse, then yx is where?
R.
It's in R, so therefore that's in the symmetric closure. So you only have two cases to do for that. And then the last thing we'd have to do is prove that it's minimal. So we do it by contradiction again. We suppose not. Assume we can take a point out. Same exact thing as before. We can't take any out of R because then R is not a subset anymore. And we can't take any out of R inverse because then it's not symmetric anymore. So you got the same exact proof, you just have to do a couple little extra things.
Can you see how you prove it's symmetric again?
Proving it's symmetric? Well, the definition of symmetric says for all xy in the relation, that yx is in the relation. Right?
Okay.
So I have to assume I have a point xy and show that the point yx is in there.
How do you do that?
I write, if xy is in the symmetric closure, then I need to prove that yx is in there. So I would write, if I want to show RSC is symmetric, then I assume xy is in RSC. I need to prove that yx is in RSC. And I had two cases to do it. xy either came from R or it came from R inverse.
So basically, it's just kind of it's logic that you know it's an R inverse.
It's from the definitions, yeah. So everything's straight from the definitions. It's just like we did with the symmetric proof. With the reflexive proof. Okay? Okay, so that one's on your homework, which is why I didn't write the whole thing out. This next one's not. So transitive closure, we talked about being able to do it, but it's actually a little more complicated than the other two. It's really easy to look at something and figure out the reflexive closure, right? It's easy to figure it out because you know what the reflexive points are. Symmetric closure is easy because every single one you can go right under it and write the opposite. Just write the reverses right up under them. So transitive closure is a little more tricky because you have to check every single pair of elements, A, B, and BC, and make sure that AC is in there. And if it's not, you have to put it in. But then that adds another point that you have to check with everything else to make sure that it's transitive. Right?
Sounds like recursion.
So it's kind of recursive. That's right. So I'm going to tell you what the transitive closure is. It's the union, k equals 1 to infinity, of R to the k. Okay, so I actually have to tell you what taking a relation to the power means. And then we're going to come back to this definition and tell you why it's that. Okay, but let me draw a little picture first. So we said if we have A goes to B and B goes to C, then we need to have A goes to C. So if this is our original relationship, let's just say we have another point here, D, and C goes there. Okay, so if this is our original one, what do I have to add? Start adding to make this transitive.
A to C, A to D.
I need to add A to C and B to D, right?
And A to D.
But then after I add that, I actually have to, now I have to add things, because now I have A, C, and C to D, I need to add AD. Right? But now since I have A to B and B to D, I need to add A to D, but that ended up being the same thing, right? Let's see, do I need to add anything else? All the 2 hops and the 3 hops, that's good. So the red ones were 2 hops in the original relation, right?
That's red.
You can't see that it's red, probably. These were 2 hops. And the blue ones, which are on the outside, which you maybe can't see that it's blue, those were 3 hops in the original relation, right? If you look at it, the original ones was just the middle ones. And then the second layer is the double ones, and the third layer was the triples. It ended up being the same one, but if you had multiple triples, it would have... I don't have to draw it twice, but... Composition is what we're going to do next. Composition will take... If I do R compose, this is R, the things in the middle, that's my relationship R. If I compose it with itself, it's going to draw all the 2-hop jumps. So R squared is actually all the 2-hop jumps. So it would actually have AC in there and BD in there. We're going to do this, so you don't need to write anything right now. I'm just trying to show you with the picture. So R squared is going to give you all the 2-hop jumps. R cubed is going to give you all the 3-hop jumps. So when I compose 2 relations, what I'm actually doing is from the first relation, I'm taking 1 hop, and from the second relation, I'm taking 1 hop. So R composed with R is a hop from R and a hop from R together.
So is K the cardinality? Like the number of items in R?
K is how many jumps I do.
Okay.
And that's how many times I compose R with itself.
All right.
Okay, we're going to do that in just a second. Yeah, you have a question?
Why is this an R to the K problem and not like a factorial problem? Because it seems like in the end you just have to do all possible points together.
Because composition does that for us.
Okay.
That's why. So it kind of feels like factorial, but it's not exactly factorial because the way we do composition will actually do it for us. It does all the combinations for us, which is really cool. Okay? So let's do composition. Okay, so here's one relation, A to 1, B to 1, B to 2, and C to 2. And let's say that S one goes to X, and 2 goes to X, and 2 goes to Y. So I can draw these 2 relations. So if I draw R, then I would draw A and B and C. I know you can't see that very well. And I would draw 1 and 2. And then I would draw arrows from the left sets, the left points to the right ones according to whether there's a point in there. So A goes to 1. B goes to 1, B goes to 2, and C goes to 2. Now we can draw S. S goes from 1 and 2 to X and Y. So 1 goes to X, and 2 goes to X, and 2 also goes to Y. Now remember I told you on the first day that we talked about binary relations that we could actually do something called a composition to get all the 2-hop flights. Remember that? That we said we wanted to find out all the non-stop flights and then maybe 1 stop and then maybe 3 stops. Well, composition is going to give us, if we combine 2 things, it'll give us all the 2-hop flights. So if R is flights from these cities and then S is flights on another airline maybe, then these are all the 2-hop jumps we can take where the first hop is from R and the second one's from S. Now the only funny thing about this is the way we write the composition. So do you guys remember composition in calculus? No?
No.
If you have in calculus, if you have F composed with G, you actually have to do G of X first and then do F. Remember that? If I have F composed with G, I have to do G of X and then take F of G of X. It's kind of irritating. Okay, so the way we write composition is going to be just as irritating here because mathematicians made it up and we have to do it that way. Okay, so we're actually, if we want to start with R and then do S, we actually have to put R on the right. So the rightmost one, when we're doing composition, the rightmost one is the one that actually we do first. So if we want to start with the A, B, C and get to the X, Y, we have to do R composed with S, which is written S, circle R. So this is doing R first, so do R first. So when you look at the picture, you just reverse these. We go from R to the middle set and the middle set to S. Would this work if the middle sets didn't overlap? No. So if there's no overlap of the points, so if R went from A cross B, then S has to go from B to something. Sorry, this you guys can't even see this. So it has to go somewhere else. Right, so it has to be B cross something else. So those sets have to overlap in order for us to do composition at all in the first place. Because we don't want to get stranded, right? It'll just be totally empty if everything, if R was A cross B and S was C cross D. Wouldn't work. Okay, so we need them to overlap in order to do composition. So here, what are going to be the points in R composed with S? If I take one jump from R and one jump from S, then what do I get?
A to X.
I'm going to go A to X. What else? I'm going to go B to X. What else?
C to Y.
C is going to go to X.
B to Y.
And B is going to go to Y. And
C to Y.
C is going to go to Y. So it's not too hard with the picture to do composition. You can just look at it and follow all the arrows. The only tricky part is making sure that you did follow every single one of them and do all the combinations. So now you can kind of see how it already does some factorial stuff, kind of things, because we're doing all the combinations of all the arrows.
So those make up the set.
This is the set R composed with S.
Which is the set we need for transitive closure.
Right. For transitive closure, I'd do R composed with R. So I would actually do R twice.
Why do you say R composed with S and not the opposite way around?
That's just the definition of how I do it. I say R composed with S. R comes first, so I actually have to write R on the right. That's the way composition is. It's just like that F composed with G thing. You have to do G first and then do F. If I have this here, I have to do R first and then do S. So whichever one I want to do first, that goes on the right. And then the next one comes after that, on the left. Okay, so let me write a definition of doing composition. Because it's going to look, you're going to think this is kind of cool. It's going to look kind of like the definition of transitive. Okay, so if I want to compose R with S to get R composed with S. So what that set is equal to all the points AC so that AB is in R and BC is in S. So if you take a look at that for a second, it'll make sense with the picture that we just drew. The first point comes from R, and the second point comes from S. And then if I have AB and I have BC, then I'm going to get AC in my final composition. And that looks a heck of a lot like the definition of transitive, right? If I have AB and BC, then I should get AC in the relation. So that's actually going to help us with finding whether something's transitive or not. So if I do R composed with R, then that is the set of ACs so that AB is in R and BC is also in R. Now that really looks like transitive, doesn't it? Because this is actually the left-hand side of my implication in the definition of transitive. When I have transitive, I have to say, for all A, B, and C, if I have A, B, and R and BC and R, that implies that AC is in R. So, and R composed with R has all of those AC points, every single one of them, no matter what A, B, and C are. So another way to write transitive, so this is one way to write the definition of transitive. Another way to write it, if all of these points that are in R composed with R, if they were in R to start with, then I'm already transitive. Right? So if all the points that look like this are already in R, then I'm transitive. So this is also written as R squared. The 2 tells me how many times I compose it with itself. So another way to write the definition of transitive is that R squared is a subset of R. So in a way, this makes it a little easier to check transitive. Instead of having to check every single pair, you can do the composition and write down all the pairs, and then you can just check and see if they're there. And it's easy to double check that you've done the composition, especially after I teach you how to do it with matrices. Because with matrices, it makes it easier. So these 2 definitions are logically equivalent. Both of those mean that it's transitive. If this is true, then the relation is transitive. If that's true, it's transitive. It's both the same kind of definition. So we've drawn pictures for binary relations. The next thing we need to do is write matrices. So how many people are familiar with matrices at all? Okay, so you've seen some matrices, and you know that if I write an ordered pair, then I would write the row first and the column second for a matrix, right? So since I have ordered pairs and relations, I can represent them with matrices. Okay, so we're going to come back to composition. Composition is probably the hardest part of doing this binary relation stuff because we have to do lots of compositions. And so you'll need to practice with that. So I can represent any binary relation in a matrix because I can put one set down one side and the other set across the top. And then I'll be able to write a 1 if I have the point in the relation and a 0 if I don't. That's just like we were writing Remember when we did the power set of a set, and then we put a 0 if we didn't have that element in there, we put a 1 if it was in there? That's what we're going to do here in the matrix too. It's going to be binary. So in this case, if I have R is a subset of A cross B, then this goes on the rows. The first one is the rows, and the second one is the columns. So let's say A is the little letters A, B, C, and capital B is going to be the numbers 1, 2, 3. So this is going to be a 3 by 3 matrix where the rows are labeled with A, B, and C. So the other day we asked the question, how many possible relations are there given a cross product? And we said it was 2 to the size of the cross product, right? Yeah, because all the possible relations is actually listed by the power set for the cross product, right? So the power set for the cross product has 2 to the power A, the size of A times the A size of B, right? Well, this actually shows us why. Because these are all the elements of A, these are all the elements of B. How many elements are in this matrix? 3 times 3, which is the product of the sizes of the sets, right? Now, the reason where the 2 comes into play is because each of one of these can be a 0 or a 1. And any combination of those will be a binary relation. So each one has 2 choices, and I have 3 times 3 blanks. I have 9 blanks. So the number of possible relations is 2 to the 9th. Okay, so let's make the simplest example of, this isn't reflexive, so let's just make some example relations here. If we have A, B, C, 1, 2, 3. That's a binary relation, right? And so if I have this matrix, which I just made up, I can draw a picture for it, right? Or I can write the points down. So these are things that you want to practice doing. You want to be able to write the points. You want to be able to write the picture. So this has the point A1. I read from the row and from the column to tell which one has a 1. And I only write down the ones that have 1s, and I don't write the ones that have 0s. Kind of reminds you of the midterm stuff we did, doesn't it? Okay, so we only write down the ones with 1s. So we have A2. We also have B2. And we have B3. We have C1 and C2. So we can also draw a picture with this. If I put A, B, and C, and 1, 2, and 3, then I have A1, I have A2, I have B2 and B3, and I have C1 and C2. So this is called a graph or a digraph because it's a directed graph because all of the arrows have directions on them. You can have graphs that don't have arrows. You can just have lines, which connects things, which really means the arrows go both ways. So if you have lines with no arrows, it means it goes both ways. But if any of them have arrows, then all of them should have arrows, and then it's called a digraph. Okay, so these are the three ways to write this relation. I can write it down as a set, I can write it as a matrix, or I can write it as a picture. Now, I don't do the transitive closure for something like this because we only have those properties for relations that are on sets that are crossed with themselves. So things like S cross S or A cross A. So this I wouldn't do like the transitive closure or anything because I can't talk about it being transitive. Okay, but let's try a composition with two relations, with a matrix. So first we're going to do it with the points, then we're going to do it with the matrix. Let's see, what was that one that we had before? S and R. Here we go. This is what we have. We had A1, B1. Now let's put these in matrices. Okay, so we already figured out the points for that, so we're going to double check our work. We're going to put it in a matrix and do matrix composition, and I'm going to show you how to do it. So first let's make the matrix for R. We have to put A, B, and C down one side and 1 and 2 across the top. So we have a 1 in A1, a 0 in A2. In B1 I have a 1, in B2 I have a 1. C1 has a 0, and C2 has a 1. And then for S, we actually usually put matrix sub R, matrix sub S, so big M for the matrix. So S has to have 1 and 2 for the rows and X and Y for the columns. So we have 1 goes to X, and we have 2 goes to X, and we have 2 goes to Y. So there's our matrices that we want to work with. So we can check these just the same way we check the points if we want to. So let's do that first. So what I have to do is I have to go from A to anything I can go to and then see from that point which one I can go to over here. So A goes to 1 and then 1 goes to X, so I get AX, right? So my final matrix should have A, B, C down the side and X, Y across the top. So AX is true because I just went from A to 1 and 1 to X. Now A can't go to 2, so I don't need to do anything else with my A. So I know it can't go anywhere else because 1 couldn't go to Y, right? So I can go ahead and put a 0. A doesn't go to Y. Now let's check B. B goes to 1 and 1 goes to X. So B goes to X for sure. 1 doesn't go anywhere else, so I can't put anything for Y yet. So now B goes to 2, and 2 goes to X and to Y, so actually B goes to Y also. I can check the next one. C goes just to 2, but 2 goes to both X and Y, so C can get from X to Y in the composition.
You said C can't go to 1, right?
So this is the matrix. Now this is really going to blow your mind, and I hate this, but I'm going to have to do it. This is the matrix for S composed with R. When I do matrix composition, hang on just a second. This is also written as the matrix for R times the matrix for S. Because you put the matrix for R first.
Times across.
It's really, it's really a circle. It's matrix multiply is what it is. We're going to do matrix. We didn't really do matrix multiply. We just did it point by point. But for C, we went from C to 2 in the first relation, and then we went from 2 to X, so C goes to X, and then we went from 2 to Y, so C goes to Y also. Okay, who knows how to do matrix multiply? Anybody?
I used to.
Used to, yeah.
Okay, so let's look at it from this example. In a matrix multiply, I take each row by each column. Okay, so let's do it row by column for this problem right here. I take the first row by the first column to get the 1, 1 element, or the A row by the X column to get the AX element. So if I wanted to get BY, I have to take the B row times the Y column. Okay, so that kind of makes sense. Let's look at it. So what I do is I take this row and I write it as a column. I write the other column right next to it. So this is the A row written as a column and the X column. Then I multiply these and then I add. Because I don't care whether I go from A to 1 to get to X, to A to 1 to X, or A to 2 to X. It doesn't matter to me which one. So this one right here is actually A goes to 1 goes to X. This is A goes to 2 goes to X. Right? Because this element right here was A1. This element right here is A2. This element right here is 1x, and this is 2x. So I don't care which one of these, so it's an OR here. This plus is actually a binary OR. And the times is really AND, but times and work exactly the same. The plus, the only difference between regular plus and binary plus is that when you add 1 and 1, you get 1. Right? We don't get 2, we get 1. So 1 times 1 is 1. Add that with 0, we get a 1. That's why we got a 1 in our matrix right there. When you get used to row and column multiply, you won't have to check element by element just like we just did. But before you get used to it, it might help you to write these columns out like this. If I want the AX element, I write down the A row as a column. And you actually have to do it left to right, so left goes to the top. Okay, so I read it this way and I write it down that way. Over and down I read the same way. So then I write the column for X, and then I multiply element by element, and then I OR the whole thing. Okay, so now if I want the AY element, then I have to write the A row and the Y column. So the A row is 1, 0. The Y column is 0, 1. I do a multiply. So this would have been A goes to 1 goes to Y. This would have been A goes to 2 goes to Y. Neither one of those works, right? Because 1 doesn't go to Y and 2 doesn't go to Y. Or 2 does, but A didn't go to 2 in the first place. So neither one of those works, and I get a 0. And that's what we got in our matrix. Okay, so you'll do that just row by column, row by column, row by column, every single one. Who wants to know a trick to make it faster?
I do.
Good. Okay. Now this requires a little imagination. Okay? The imagination is you have to think about magic wands. All right? You have a magic wand. And your magic wand is actually this row right here, the A row. So I want to get the A row in my new matrix. So I'm going to pretend this is magic wand. I'm going to turn my magic wand like this. Okay? Now, I think of it as a magic wand because I'm going to pick it up and I'm going to sweep it across the other matrix and I'm going to pick up things with it. Okay? The only place I'm allowed to pick up things, though, is where I had a 1 in the original row. So if you go back and look at what we just did, the only time I could possibly get something from one of these columns is if I had a 1 in the A row in the first place. Right? Because otherwise I'm going to get 0 and I can ignore whatever's in that column. So I'm going to think of this as a magic wand, and wherever there's a 1, I can pick up the stuff from the column. So this black part is my 1, and the white part is my 0. I'm going to sweep it across the second matrix to get my A row. Okay? So I sweep it across, and I pick up any row that has a 1. The black one was a 1. So it's going to pick up 1, 0. It doesn't pick up the other row at all. Right? They put a 1, 0 right there. Isn't that cool? Let's play magic wand with the second one. Okay? The second one has 2 1s. Okay, so it's going to pick up everything, right? It's going to pick up both rows. So I turn it, I take it, I turn it, and I sweep it across. It's going to pick up both of them and OR them together, element by element. So to OR these two and OR these two to get the next row, to get the B row. I started with the B row, I'm going to get the new B row down here. So I sweep it across, I get that one, and I OR them together, I get 1, 1. That's what I got right here.
Can you do the first one again?
In a minute. I'm going to do the whole thing over again, but I want to finish first. Okay? Now here, my magic wand is white and black, right? So I can only pick up the black one. I turn it sideways, it picks up the second row, which is 1, 1. So this is a 1, 1 also. If you don't get it, you don't have to use it. Eventually you'll get it. You will, because you'll do enough of these and then you'll go, oh, that's what she's talking about. Okay, let's do it again. So the first one is a magic wand. The 1 is what's going to pick stuff up. So I rotate it, and wherever there's a 1, I'm going to pick up what's under it. Okay, so that 1 picks up 1 and 0.
The 1 and the 0.
The 1 and the 0. I'm picking up this row. Okay, if you don't get it, you don't get it. There's nothing I can do to help you until you practice.
1 and 2 as the row, or just...
I'm looking at this row right here.
So just
I'm trying to get this
what's
row.
under the X and what's under the Y.
This is a row.
Okay.
1, 0 is a row. 1, 1 is a row. These are rows going across. I'm taking this and sweeping it across and picking up stuff in the row. Okay, wherever there's a 1, I'm going to pick up that row. So I pick up this row, stick it right there. This 1, 1 picks up both rows and ORs them together. That gets put right there. This third one picks up just the bottom row and puts 1, 1 over there. Okay, maybe it'll help you to see this a little better if we do an identity matrix. Okay, if it doesn't make sense, it's okay. You do not have to use a magic wand. You can do any way you want to. Okay, it's not required to do Tiffany's magic tricks. So if I have any two matrices, if I multiply by what's called the identity matrix, I will get back the matrix that I multiply it by. This is called the identity matrix, and anytime we have an operator and we can multiply by something, do that operator with something and get back something else, the same thing, that's called an identity. So for multiplication with regular numbers, what's the identity? 1. If I multiply anything by 1, I get back the number that I multiplied it by. So for ANDing, what's the identity? 1. So in binary AND, 1 is the identity. What about OR? What's the identity for OR? 0. So the identity for a regular addition is 0. Okay, so we have an identity for most operations. Not necessarily all of them, but for lots of them we have an identity. If we take that identity and do the operation, we'll get back the thing that we do it with. Okay, so let's figure out why this gives us back A, B, C, D back. So doing the magic wand trick, we only have 1, 1 on there, so it's easy, right? If I do the magic wand trick, I take this, I have a 1 on top, I turn it sideways, sweep it across, I get A, B. Magic wand trick with the second one. I have a 1 on the second row, so I pick up the second row, so I get CD. If you do it element by element, I promise it comes out the same way.
So all you have to do is a number. If you pick up a whole row, if there's 2 1s in there, you have to end it with the next one.
Or.
That's
right. So if I actually had, let's do this. So regular matrix multiplication just doesn't do binary. It does regular multiplication and addition instead of ANDing and ORing. So let's do this times A, B, C, D, and we'll see what we get. So if we do magic wand here, this first one actually has 1, 1, so I'm actually going to have to or add those 2 rows. So A plus C goes in the first element, B plus D goes in the second one. And this last one just picks up the bottom row, so that's CD. So because this one picks up the first row, this one picks up the second, and they have to be ORed together or added together. Or add is the same thing. So it just depends on whether you're doing binary or regular addition.
Between the two matrices, don't you need that multiplication sign, that cross product
No,
sign?
if I write them next to each other, that implies that I'm actually going to do composition, matrix multiply. Okay, if I take two matrices, if I want to do the union of two relations, I can take their matrices and do element by element ORing. So is this okay for everybody? If you don't get it, just practice. You will get it. It's row by column, element by element. So you have to pair up the elements. Just look at it, you'll be able to get it. Okay, so if I want to do the union of two sets, if I have A union B, if I have the matrix for A and the matrix for B, so I can do a matrix union, then it's element by element. 1 union 0, or, that's actually an OR, right? I have to do an OR. So do That gives me a 1. 0 or a 1 gives me a 1. 1 or 0 gives me a 1. 1 or 0 gives me a 1. So union is element by element OR. Intersection is going to be what?
Where they overlap truths.
It's going to find where they overlap. So if I did these two, I'd get all zeros, right? So it's an element by element AND. So if I did these two together, the 1, 1 element is in both, but the 1, 2 is not. The 2, 1 element's not in both, so that gives me a 0, but the 2, 2 is in both. So if we do an intersection, that's an element by element AND. If I did an exclusive OR, it's an element by element exclusive OR. So the way the set definitions work is the same way we do with the matrices, element by element. The only thing that isn't element by element is composition. That's row by column. Everything is row by column for composition. Okay, so with the last couple minutes that we have, what does a reflexive relation look like if it's in a matrix?
Diagonals.
So what elements are absolutely necessary in this to make it reflexive? 1, 1, and 2, 2. So anything that has 1s on the major diagonal is reflexive. So it doesn't matter what the other things are. Could be 0 or 1 in either one of those places. But anything that looks like that is reflexive. How about an irreflexive matrix?
Doesn't have. It
Has to have what on the diagonal?
Zeros.
Zeros, because it can't have 1, 1, and it can't have 2, 2. It doesn't matter what's on the outside. So what does a symmetric matrix look like? It doesn't matter as long as the top triangle looks like the bottom triangle. So I have 3 parts to a matrix. I have a diagonal, upper triangle, and lower triangle. When I talk about the diagonal, I'm always talking about the one that goes from the top left to the bottom right. That's the major diagonal. I don't even know what you call the other one because we never ever talk about it. It's what? The minor diagonal? I don't know what it's called. Okay, so if the upper triangle, if I fold it over, the upper triangle and the lower triangle are the same, but it's folding over because they're the mirror image. So these have to be mirror image. So it's easy to check. The diagonal, it doesn't matter what's on there. It can have anything. As long as the upper triangle and the lower triangle are the same, it's symmetric. So how about anti-symmetric?
A upper triangle and lower triangle have to be different.
Okay. If there's a 1 over here, it has to match with the 0 over there. If there's 0, 0 is okay. So 0, 0 is all right. But if there's a 1 on one side, it has to have a 0 on the other side. So if I'm looking across the diagonal, the mirror image, so if I have 1, 3, that means that 3, 1 is not allowed. Right? Asymmetric means I have to have all zeros on the diagonal, and I can't have anything like this either. It has to be anti-symmetric, and this diagonal has to be zeros also. Now, transitive, you can't look at a matrix like this and tell. Transitive, you have to do the composition of the matrix with itself and check to see if those points are in the set originally. And I have all of these things in your notes pretty much. So if you print out the packet, those will be in there. And I'll see you guys next time.